You're welcome to this class. Once again, I said good evening to everyone. This is our fifth lesson in Chem 307, Atomic Molecular Structure and Symmetry. Today, we will be looking at atomic spectra. We'll be looking at atomic spectra. And from the slide before us, we'll discover that the emission spectrum of hydrogen has been divided into a number of spectral lines with wavelengths given by the Rayburn formula. And these observed spectral lines are due to the electrons making transitions or moving from one energy level to another in the atom. If you remember in one of our previous class, we mentioned about the atom being in a ground state and the atom being in an excited state. The atom being in the ground state, that's when it is stable, and it will require some additional energy to move the electrons to an excited state. So when the electrons move from the ground state to the excited state, there is always an energy involved in this very particular transition. Now, the classification of the series by the Rayburn formula was important in the development of quantum mechanics. And the spectral lines or series are important in astronomical spectroscopy for detecting the presence of hydrogen and calculating their rate shifts. When an element is heated in a flame or a discharge of electricity is passed through a gas, colors of light, which are characteristic of the particular element, are actually reflected and are seen or viewed by by the by the by the eye. For example, the discharge tube containing neon gas at low pressure can glow. It glows red, while sodium light emits yellow light, and mercury gives green glow as it is. Now, the atomic spectra is when a light generated from the element by heating or from a gas as a result of the passage of the electricity, which is passed through the spectroscopy, it produces a spectrum which is known as emission spectrum. And these emission spectrum are usually peculiar or a characteristic of a particular element. Now, Rayburn tries to give a formula that relates this that we are talking about, that the wavelength or the frequency is 1 over lambda, which is equal to open bracket 1 over n2 square, close bracket, minus 1 over ny square, close bracket. Or in other words, the energy which is involved in form of photon, which is equal to ER, is equals to Planck constant V, which is hc over lambda, where h is the Planck's constant, c is the velocity of light, and the lambda is actually the wavelength. Now, the Rayburn formula gave a series. The series, which is the slide that you can see before you now. You have the Lyman series, the Balmer series, the Paschen series, or in some books you see as Bohr series. The fourth is the Brackett series. The fifth is the Font series, the Humphrey series, and the Fodor series. Now, when n in the formula I gave you earlier is equal to 1, then that is the Lyman series. If n is equal to 2, it is the Balmer series. If n is equal to 3, it's the partial series or the Ball series. And when n is equal to 4, it is the bracket series. When n is 5, is the Foot series. And when n is 6, is the Humphrey series. And when s is greater than 6, are further series which we may be able to get to them later or in the due course as we continue with the study. Now, the atomic spectra, as we said, is when light generated from the element by heating or from a gas as a result of the passage of electricity through a spectroscopy produces a spectrum known as emission spectrum. The emission spectrum that the emission spectrum which is produced, the emission spectrum which is produced, the emission spectrum which is produced tries but produces a color of the light or characteristic of the light which is actually seen in the series or as a series of lines which are called spectrum or atomic spectra. Each element gives a unique pattern of spectral lines, and each line has a distinct length or wavelength. The atomic spectra of the elements are heavier than hydrogen and are considerably more complex. That is, the atomic spectra of heavier elements or elements with greater atomic weights are more complex than that of hydrogen. But for the illustration of the particular course we have today, and for better understanding, we will actually concentrate mainly on the spectra of hydrogen as an atom and what comes out of it. Now, from what we know, you said that there's an energy gap. When an electron is excited, like we said in the other class, there is a photon or an energy that is released. Now you have the baseline and you have the upper line. Now the energy gap that is released between the two is what you actually call the photon, and that gives you the characteristic lines that you see in the atom as indicated in one of our class before. And as I also said before as well, you have the ground state, you have the excited state. The atom at the ground state is normal, is stable, is not reactive at that state. But once it is excited, that is, there is an additional energy that is given onto it. Now, these electrons are excited to the excited state. The energy difference between the two as it races again to come back to the ground state is what you call the photon. And that gives a characteristic lines, which is called the spectrum line. Absorption of energy, the absorption of energy actually makes the atom electron jump from the ground state to the excited state. On transition back to the ground state, the energy earlier absorbed is released in form of emitting a photon. By the law of conservation of energy, the energy loss by the atom in transition from excited back to the ground state must be equal to the energy of the photon. So this leads to the formula delta E is equal to E transition, which is equal to HV, which is equal to H over lambda, which was the formula I gave us before, where H is the Planck's constant, C is the velocity of light, and lambda is the wavelength. This shows the relationship between the wavelength of and the emitted light and the energy difference between the ground and the excited states of the atom. Now, in the spectrum of hydrogen, atomic hydrogen has only one electron, hence the simple nature of the emission spectra for it. It displaces several lines in the visible and in the infrared and in the ultraviolet regions. The lines are fitted by the Rebanks formula, which I gave us before. And if you also look at the slide that is before us, that also tries to give us an illustration of what we are also talking about. You see where you have the N1, N2, N3, and N4. As I told us earlier, that each and every one of them stands for a particular spectra of line. You have the Lyman series, N1, you have the Balmer series, N2, you have the Paschen series, and so on. Now, you also have the wavelengths, that is from 112 nanometer to 194 nanometer, which falls along the Lyman series. You also have from 410 nanometer to 656 nanometer, which falls in the Balmer series, and the 109.4 nanometer to 1875 nanometer, which falls in the Balmer series, and so on and so forth. You see the same illustration as shown here in a more better way that you can actually appreciate them. This is the Lyman series, the Balmer series, and the Paschen series, next the Hood series, and the rest of them. So these are characteristic lines that falls within the spectrum of the electromagnetic spectrum. Now, each of them, particularly those who falls within the visible region, gives you a characteristic color. You see the Lyman series around 100 nanometer, and something, is it gray or yellow? I don't know how to describe that color better, but you can see the color there. You go to the Balmer series, the Paschen series, the Bracket series, the Foot series, and the rest. So these are the spectral lines of the hydrogen atom as it continues to emit electrons inside this thing. If we go to the next slide is still an illustration. That is the energy level diagram of electrons in the hydrogen atom. You see the N1, which energy is around minus 13.6 electron volt. N2 is around minus 3.4 electron volt. N3 is around minus 1.51 electron volt. And N4 is minus 0.84 electron volt. So it gives you the energy, and those energy depends on those lines depends on the amount of energy that is actually going to the atom, and it gives you a particular characteristics as well. Now, I gave us the Laban's formula, which actually gave rise to those lines that we have there. 1 over lambda is equal to, open bracket, 1 over n2 square minus 1 over n1 square, which is where you have n1 and n2 are integers, and it is the Laban's constant. What that is, the v that is there is Laban's constant, and the value for it is 1.0970 times 10 to the power 5 per centimeter. And the spectrum of the atomic hydrogen have all the lines that are actually required. I intend actually bringing out the spectrum of those lines for you to see, but to be honest, drawing them was a little bit difficult. But if you can take note, let me make some few explanation or clarification on that. Now, those belonging to the given series with a common value of N2, but different values of N1 are as known. When when the series is Lyman, it means the N2 is 1 and the N1 starts from 2. That means the region in which this very particular spectrum will fall will be the ultraviolet region, and the wavelength is around 1.21.3 nanometer. The next one, when N2 is equal to 2, that is the Balmer series, as we saw in our earlier slide. The Balmer series means N2 is 2. So your N1 starts from 3, 4, 5, and 6. This falls within the visible region of the electromagnetic spectrum, and it is around 656.3 nanometer. The next is the Persian series, where N2 is 3 and N1 starts from 4. This falls within the infrared region of the electromagnetic series, and the wavelength is around 1875. Now you have the bracket series, where N2 starts from 4 and N1 starts from 5. This is also infrared, and the wavelength is around 4051. Then you have the Hood series, which N2 is 5 and the N1 starts from 6, is also infrared, and the wavelength is around 7458. And these are series of atomic hydrogen, which burns at various stages of the listen as energy is actually applied. Let me give you a question which you take as a homework and you do. And in our next class, we shall discuss it. One, calculate the wavelength. Calculate the wavelength. Calculate the wavelength of the visible line in the hydrogen spectrum that has the longest wavelength. Calculate the wavelength of the visible line in the hydrogen spectrum that has the longest wavelength. What is the energy difference between the two levels of the atom involved in the transition, giving rise to this through line, giving rise to this line? Let me take that again. One, calculate the wavelength of the visible line in the hydrogen spectrum that has the longest wavelength. What is the energy difference? What is the energy difference? What is the energy difference between the two levels of the atom? What is the energy difference between the two levels of the atom involved in the transition, giving rise to these lines? Giving rise to these lines. Giving rise to these lines. I will take the whole question again. Calculate the wavelength of the visible line in the hydrogen spectrum that has the longest wavelength. What is the energy difference between the two levels of the atom involved in the transition, giving rise to this line, giving rise to this line, giving rise to this line? In conclusion of our study today, we have seen that radiation produced from elemental emission consists of a complex mixture of wavelength. We have seen that radiation produced from elemental emission consists of a complex mixture of wavelength, which can be dispersed into its various individual components by means of a spectrometer. The observed spectra are made up of sharp lines. Observed spectra are made up of sharp lines, which imply that the energy of the atoms and the molecules responsible for such lines must be discrete rather than continuous, which implies that the energy of the atoms and molecules responsible for such lines must be discrete rather than continuous. Atomic hydrogen has one electron, hence the simple nature of emission spectrum that it has. Atomic energy of hydrogen has one electron, hence the simple spectrum that it has. Hence the simple spectrum that it has. Once more, I thank you for the patience and for the way you were able to listen patiently to this very particular class. I enjoin you to join again in our next class, probably on Saturday. We will be able to discuss more on these very particular issues. Please, while coming, try to come with your notebooks and your writing materials so that some exercises can be done and we can also interact with each other on this very particular platform. Thank you.